What is our objective? Our objective is to convert this C++ program into what? Assembly. Okay. Now please remember, in the previous example we implemented some conditional statements. We implemented some conditional statement, if and else statement in assembly. Yeah, we did. But now what we are going to do, we are now converting a more complex C++ program. So this is a C++ program, and now we want to convert this C++ program into assembly. Okay. Now if you look at here, so now what we are going to do, we are adding all the elements of the array and store it in a variable sum. Okay, now if you look at here, where sum is mapped, look at this thing, where sum is mapped, to which register? R3. So it means that now, what is now our assumption for this program? So now in this program, sum is now mapped to register what? R3. Clear? In this example, sum is now made to register R3. Okay, now we have some loop variable. We have a loop variable. Okay, this loop variable, what is the name of that loop variable? No, loop variable, not loop. K. K is now our loop variable. So now sum is a register which is mapped to register R3. Now we have the loop variable K, which is mapped to which register? Help me. Which register? R2. So now K is now mapped to register R2. First we need to make an assumption. In the exam I will give these assumptions and you have to write a program. We can change the code or something like that. Okay. Now that we have some array. What is the name of the array here? A. We have some array A. So now the name of the array A is actually, what is A? A is now the name of the array. What is A? So now we can say A is the name of array. What is the name of the array? Name of the array is a constant pointer. Name of the array is what? A constant pointer. Now if you look at the memory, what is the constant pointer in this example? What is the constant pointer in this example? Look at the memory there. That's something. So the name of the array is a constant pointer, and the base address of the array in this example, what is the base address of the array? Help me. No, the base address of the array. Look at the. This is my array. This is data. This is my array. What is now the base address of the array in this example? 3100. So this is what? The base address of the array. This is now my A. This is now the base address of the array. Okay. Now the question is that which register is pointing to the base address of the array in that example? Which register? R1. So it means that now we have some register R1. And now what should be the content of this R1? What should be the content of this R1? Help me. What should be the content of this R1 at the start? The address. What is the address? R1. So basically A is the name of the array. It should be mapped to R1. And if it's mapped to R1, what should be the initial value of R1? 3100. So the initial value of R1 should be 0x3100. Clear or not clear? Clear? Okay. Now, so what we are going to do, and now. Okay, now we want to write a program. Okay, please remember, there are two portions of the program. The instructions are shown in which color? Help me. Red color. The data is shown in which color? Huh? The black color. Okay, now, if you are having the instructions, so basically now what I am going to do, I am now going to write it here. It's not moving. It's okay. So should I write? What should I write? Because I am starting with the instruction. ORG. What should I write here? What is the starting address of the program? 0x 3000. Am I right or not? Okay. This is my starting address of the program. Okay. Now we have the starting address of the data. This is my data now. This is my data. What should be the starting address of the data? What should I write here? Help me. I'm using the black pen. 0x what? 0x 3100. ORG 0x 3100. So this is now the starting address of the data. Okay, now if you look at data here, so what will be stored in the first location? What will be stored here in the first location? A0. So A0 will be stored in the first location. After that, A1. After that, A2. Clear or not clear? Okay, now the problem is that, okay, now let's assume I'm now giving a label to it, because now this is okay. If you look at A0, we can assign some label to it. So I can call it as base. Base address. And what is the base address of this array? What is the base address of this array? Help me. 3100. So this 3100 is my what? Help me. Base address. This is not my base address. Please remember, we will use all of the concept that we used in our lecture slides. Okay, now, okay, what is our objective now? Our objective, so now basically if we want to do, so what is our objective? What is our first task? The task number 1. So this is my task number 1. Task number 1. What is my task number 1? Our task number 1 is to load what? Load the base address of array, into which register? Help me. Into which register? R1. Which instruction should we use? Please remember. Now that is the thing, because now you studied all of the instruction. Should you use LD, LDR, LEA, LDI, ST, STR, ST? Anyone can answer. We want to initialize this register R1 with a value of 3100. What should I use? Help me. LEA. So what should I write here? LEA what? Help me. So this basically this is my start. So now this is my label start. This is the start label. And what should I write here? LEA what? Help me. R1. Comma what? Base address. Clear? So if you say the base address, my base address is please remember, my base address. So this is my base address. So the base address is what? If you look at here, this base, the address of this base address is what? Tell me. 0x what? 3100. Then 0x31 what? 01. Then 0x31 0 and so on. Clear or not clear? Any question? Okay, now this is our first objective. Another objective. If we have the base address and we want to convert this into a binary format, so we need to calculate the offset. Okay, if we need to calculate the offset, so now we are going to do the offset. How can we calculate the offset? Help me. Offset is what? Help me again. Target. Very good. Minus incremented PC. What is my target? 3100. So 3100. And what is my incremented PC? 3001. You got it or not got it? So now we need to calculate the offset, and if you do that, please remember, if you do the math, all of these math, so we can say, so basically we can say, if you do the math, so you need to convert this into 2's complement and blah blah blah. So this will give me 0x f. Okay, I'm not going to details of that. Why? And now can you see here? So now what is now? Okay, now what will be my target? Yes, what will be my target? Help me. I'm not doing it. Target is what? Offset plus incremented PC. So target will be offset plus incremented PC. What is my incremented PC? Help me. 3001. And what is my offset? FF. Okay, we take the tools complement of this, and if you do that, so this is F, and 0, 0. If we add both of them, what is F plus 1? 0. Here's 1. F plus 1? 0, 1. Then 1. The offset is positive or negative? Positive. Because there is 9 bit for the offset. So the offset is now what? Positive. So we can also write this instruction like this. Instead of doing this, so we can write this instruction like this. Either we can use a label here, or you can use what? How can we write it? LEA, what? Help me. R1, comma 0. These are two ways to write this. Any question? Okay, now what should be my second instruction? Okay, now please remember, now we have a variable. What is the name of the variable? Sum. We need to initialize it to what? 0. We need to initialize it to 0. So what instruction should I use? Help me. And very good. And what? Where sum is mapped? Sum is mapped to R3. R3. Okay, now then we can use a loop variable. We can use a loop. How many times we need to execute this loop? How many times we need to execute this loop? 12 times. So we need to initialize the loop variable with a value of what? 12. Okay, we want to, let's do here, we want to access the first element, loop variable is 12. Then it becomes what? 11, then 10, then 9, then 8, 7, 6. And when we reach it here, what should be the value of the loop variable? 0. And when it becomes 0, it means the loop is now what? Khalas. The loop is now khalas. Clear? So basically we need to use a loop variable. And now what is the loop variable here? K. And K is R2. So again, what should I write here? Add what? Add what? R2. R2. Add 0. Okay? And then what should I write here? Add what? R2 hash what? Add, yes. Now $1 million question. This is a very $1 million question. This program is inefficient because it is using more instructions. Please remember, the code that is in the lecture slide is inefficient. So what I am doing, I am going to write an efficient code. How can we reduce the number of instructions? Okay, we can do. Okay, now what is the value of R3 here at this point of time? What will be the value of R3 here? Tell me. 0. What will be the value of R2 here? Tell me. 0. What will be the value of R2 here now? 12. How can we reduce the number of instructions? Can you tell me?
We add 12 to R3 and
instead of using this instruction, we can delete this instruction. Because now, can we see? If you do, okay, now this is inefficient code or inefficient code? Inefficient code. Since this is inefficient code, so if you want to do the efficient code, so what we will do here, the efficient code. So now please remember, what I am going to do, because you know this is the code that is already there in the lecture slide, so I can replace this instruction with this instruction. So basically what can be this here? And what? R3 has 0, and then what? Add what? R3 hash 12. Which implementation is efficient? The left one or the right hand? The left one. Clear? So in the exam I asked, write the minimum number of instruction and minimum number of registers. So you have to write an efficient code like June. Any question? Should I proceed? Okay, then. Okay, please remember that this is an inefficient code, but still we are doing it with that. So, clear, say? Can you see? This is inefficient or efficient? Inefficient. This is inefficient or efficient? Inefficient. So basically, it's in the lecture side. So that's the reason that this is an inefficient code. But still, remember why I'm making a lot of having different codes. Why I'm doing different codes? Because you need to write an efficient code in the exam. Clear? So if there is some solution in the lecture side, it doesn't mean that that program is efficient. For that, you need to attend my lectures. Okay, now, clear or not clear? Any question? Okay, now, what is another objective? Okay, now, what should we do now? So we want to have a loop. Now loop is a label. Can you see here? PRC is it. Which flag are we checking? Zero flag. Okay. Now please remember, when we do that R2 is equal to R2 is equal to 12. What is now the value of R2? 12. Is it 0? No. So the condition will be true or false? False. So now the condition will be false. If the condition is false, it will come to the next instruction. Okay, now what is our objective? Our objective is to find the sum of all element of the array. What we need to do? So we need to bring this A0. We need to bring this A0 into some temporary register R4. So we need to bring this A0 into some register R4. So L0 will come here. Which instruction should I use? I'm not going to show you to you because this is, forget about this. Which instruction should I use? Help me. LDR. LDR. Now we are using LDR. Okay, we are loading into R4. Where the base address is stored? R1. What is now the offset? Has 0. So now we have different iteration. So this is the first iteration. Okay, what I'm going to do, so please, I'm going to rub this off. Okay, please remember, I'm going to rub this off. So you can take a screenshot of this. I'm going to rub this thing off. The bottom thing. So you can take a screenshot of this. Because I need some space. Should I rub this off? No. So now we have the first iteration. So we have some register. What is the value register? R1. What is the value of R1 during the first iteration? Help me. 3100. And during the first iteration, R4, R1, R1 is now pointing to here. What is the value of R4 here? Help me. A0. What is the value of, now we have another register. What is the value of R2 here? 12. What is other register? R3. What is R3? Please remember, R3 is now mapped to sum. What is R2 now? What is R2 now? K. This is the loop variable. What is R4? Please remember, R4 is a temporary register. And what is R1? R1 is actually pointing an element of an array. So it is pointing to array. So pointing to an element, a particular element. After execution of this instruction, LDR R4, R1 has 0. R1 is pointing to here. The offset is 0. So this A0 will come in which register? R4. What is the initial value of R3? Help me. 0. The initial value of R3 is 0. But now we need to add sum is equal to sum plus the element of the array. Okay, what we need to add? We need to use an add instruction. What should I use? Add what? R3, help me. Yes? R3, very good. R4. We are adding R3 with R4. So if you do R3 with R4, what is the new value? Help me. A0. Clear? When we does this, what should we need to do? Increment what? We increment the base address. Okay, so we increment the base address so that it should point to the next element. We increment the base address. So what we need to do? Add what? R1 hash 1. So when we do that, so in the next iteration, what will be the value of R1 now? 0 is what? 3100. 3101. But now we need to decrement the counter by 1. What should we use? Help me. Add R2 hash minus 1. So basically the new value of R2 will be what? Now what? 11. And when should we khalas the loop? When it becomes 0. So we can say BRZ. Where should we jump? Loop. And what should be the last instruction? Khalas. Okay, now we go to the loop. We go again to the loop. Okay, so when we go to the loop, okay, still, please remember, R2 is 11, 0 non-zero, non-zero, it will go back to the loop. The condition will be true or false? False. So please remember, now we can see here, now please remember, now we say condition. So now this is my condition. So in the first iteration, the condition will be false. Now what is the value of R2? 11. Non-zero. Condition will be true or false? False. In the next iteration, what will be now the value of R4? In the case, okay, now please remember, initial value of R1 is 3100. What will be now the new value of R1? 301. It is pointing to what? The second element. And what will be now the value of R4? A1. So the value of R4 will now be A1. And now what we are adding? Add R3, R4. R3, the value of R3 is what? A0. What is the value of R4? A1. If we add both of them, what will be the now? A0 plus what? A1. Clear? And then when it is A0 plus A1, we are decrementing R1. So what will be the value of K now? 10. Clear? So this all these numbers are in decimal. All these numbers are in decimal. What will be the new value of R4? Tell me. A what? A2. What is the address? 31 what? 02. And then what will be now the value of R3 here? A0 plus what? Plus A2. The condition will be true or false? And it goes on. When it is the last iteration, what will be the last value? 0 is 310 what? B. When it will be 310B, because this is the last element. What will be the value of R4? A11. What has to be the value of K? 0. And then, what will be the value of sum now? Another. Any question?
Professor?
Yes.
The jump statement before the end, the BRZ to loop, it will only go to loop.
No, we are NCP.
Yeah, NP.
NCP. This is unconditional. This is unconditional, sorry.
So you're checking it twice?
No, you are only checking the condition in the start. And then when we do that, we do it true. So this is an unconditional jump. This is not a conditional jump.
You could make it BR, NP, and then it's 0.
Maybe we can do that. So you can make it an efficient program. This is your homework now. Okay? If you want to make it further efficient, so you can use BRNP instead of 2 branch, you can use 1. Okay? And you can do that. That is your homework. So basically this program is still inefficient, but you can make it more. Please remember, here, how many instructions were we using here? How many? 3. Instead of 3, we can use how many instructions? 2. How many loop instructions are there? 2. You can use it one loop, so you can make it more efficient. And this is your homework. Try it on a simulator. There are some LC3 simulators. You can try all these simulators. So what we are going to do? Okay. Now this thing I have explained this in my class, but I did all this thing with the simulation. How many instructions are there? There are total 10 instructions here. Okay, please remember, how do we calculate the offset? Offset is calculated by target minus incremental PC, and we did it. So this is the offset. This is instructions. So can you see here? So these instructions. Okay, now please remember, who will point to that instruction? Who will point to that instruction? 300. Who will point to that instruction? Program counter. Program counter will point to that instruction. This is my first instruction. Okay, what is the code for LEA? Remember, what is the code for LEA? E. This is E. And then R1. What is R1? 001. So this is 001. What is the offset? 2FF. So this is the instruction set encoding. How do we get it? From the table. And the offset, what is the offset here? Offset is 0. Clear? This is the first instruction. This is the what is the output for AND? What is the output for AND? Here, 5. What is the output of AND? 5. What is the output of AND? So these are all instructions. What type of instruction is this? This one. I type. So this is in I type instruction. So these are all the instructions and encoding. Okay. This is my memory. Instruction memory or data memory? Instruction memory, which is shown this. So this is my instruction memory. How many instructions are there totally? How many instructions are there total? There are total 10 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clear? So this is the starting address of the first instruction and this is the last instruction. Okay, now please remember, assume that this is the initial state of the processor. Program counter points to the first instruction. Assume this is the initial value of R3, this is the initial value of R2, this is the initial value of R1, and this is the initial value of R4. So we go for the first instruction. What is R1? R1 is incremented PC plus offset. What is incremented PC? 3001 and the sign extension of the offset. What will be the new value of R1? Help me. What will be the new value of R1 here now? What will be the initial value of R1? 3100. So 3100 R1 will point to the first location. Please look at here. So now R1 will point to the first location. Clear? Then we go to the next instruction. PC point to the next instruction. What is the initial value of R3? What is the initial value of R3? 2107. What will be the new value? 0. Then this instruction. What is the value of R2 initially? It will become 0. Then we add 12 to it. But 12 is actually 000C because all the numbers are in which hexadecimal system. Here the numbers are in decimal. The condition is true or false? False. Because it's non-zero. Go to the next instruction. Add here R4. R4 will contain A0. R4 now contain A0. Then add R3, R2 plus 3. So what is the value? It will become A0. Then R1 is going to be increment R1. R1 will point to the next element now. Then we decrement R2. And the loop will be the last unit which is 0. We go back here. Again, we do that and we are doing all these things. Clear? Any question? This is the third iteration. And then we have the last iteration. In the last iteration, so basically equivalence is not taken. Here, unconditional jump. The condition is now true. And then any question? And how do we convert this? So this is all the opcodes. These are all the opcodes in LC3. Can you see here? Please look at here now. How many instructions were there? There were 10 instructions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What was the first instruction? LEA. What is the code for LEA? 1110. How do we know it? From the table. So these are all the opcodes. Please remember, opcodes are 4 bits. So this is the output for LEA and. This is the output for BR. This is the output for LDR and this is the output for BR. And we know all these outputs from where? From the table. And please remember, can you see here? What is the offset here? 0xFF. So now this is the offset. How many bits are there for this offset? 9 bits. And this is also the BR. How many offset are there? 9 bits. How do we calculate the offset? Remember? What is now the offset here? Please remember. BRZ exit. Incremented PC. This is my exit now. Where is my exit? Let's assume exit is here. This is my exit here. How do we calculate the offset? Target minus what? Increment BC. Okay, so here offset 1, 2, 3, 4, 5. So this offset is what? 0.05. This offset is FF. So FF is here and 0.5 is here. Clear? Okay, now why this offset is 0? Can you see? Hash 0. So we have 0 here. Then hash 1. Hash 1 is here. And this is minus 1. In minus 1, all of the numbers will be what? 1, 1, 1, 1. Not F. Because what? 1, 2, 3, 4, 5. These are 5 bits. So the offset will be 1F. Clear? So this offset, because this is minus 1. So this offset is what? 5 bits. 1F. What is this offset? Help me. 0, 1. 0, 0, 1. And 0 and 1F. Any question? Because in the add, the offset is 5 bits. And what is the range of the offset? From minus 16 to plus 15. Remember? So these are all the offsets. Okay, now. Then look at the other parts. Because this is BRZ. So this is NZP. So this is 0 and 0. In the last instruction, it will be NZP. So NZP, all of them will be what? 1, 1, 1. This may be the question in exam. This may be the question in your quiz too. Okay, so this is how it works. Any question? Should we proceed? Okay, so what I will give. So now what I am going to do, we will write some more programs now. More programs. And more complex programs now. And please remember all of these. And I can do lecture number 7. Yes, your time starts from now. Convert this program into assembly.